Hi, Dan.
Okay, so welcome back after the lunch break. Let me just remind you that you're welcome to ask questions during the talks, and you can raise your hand, the little blue hand in Zoom, or you can type questions into the chat box, or you can even unmute yourself and jump in. And after the talk, we'll have time for questions, and we'll go back to the gather.town setting to have discussions. So the first talk after lunch, I'm very happy to introduce Adam Oberman from McGill University. He's going to talk about mathematical approaches to deep learning, uncertainty, robustness, acceleration, and regularization. So please, Adam.
Okay, thanks. Yeah, thanks for the invitation. I see some familiar faces, or I should say mostly familiar names, since people have their names up. So hello to you guys. And yeah, let me get started. I mean, maybe just for some context, I've been sort of the last 3 years or so focusing my research more on deep learning. And it's been quite an interesting time. It's been a learning process because this, when you switch fields, you have to pick up on what's important, what people care about, even different styles of publishing with conferences instead of journals. And yeah, it's a big shift. There's a lot to learn. And sometimes it's good to be open-minded. So you can have some reactions to, let me give an example. So, there's a lot of positive results for neural networks, which is, wow, it can do this, it can do that, it can win this game, it can do translate, which is great. But then there's also the negative side, which is they don't always work as well as they're supposed to, or you don't have guarantees. And I think it's important to be aware that both things are valid. There's different settings where any solution, anytime, is valuable. And there's other times where you don't want to replace an existing method with neural networks because you can't afford the loss of accuracy or robustness or whatever. So for me, looking for research problems as a mathematician, an applied mathematician, I was really trying to get involved in this field and looking for, okay, where can I, with my training, make a contribution? And there's more and less mathematical areas to the field. So for example, optimization is essentially an area of mathematics. And one of the projects I had was on stochastic gradient descent, which I'll talk about a bit here today. And then there's other areas that are more statistical. And again, that's more mathematical. I was a little naive thinking right away that, oh, I can just take a PDE, throw it down on deep neural networks and something great will happen. And this is really a trade-off between how rigorous you want to be versus how much impact. It's not always easy to do both. In any case, I did have some PD ideas. It does come in, but what I've really learned is the most important thing is math modeling. It's really trying to understand the problems and see if you can translate that into mathematics, really stating the problems more than hard technical rigorous work. And one area you can see that in is even just the metrics. So I'll talk a little bit about normalizing flows and optimal transportation. One important thing to point out in this is that when we do GANs, we're not really solving the optimal transportation problem. We're not really even mapping one measure to another. It's well known that the maps are not onto. And moreover, the metrics that people use are loosely based on optimal transportation, but they're not even really computing that. So one of the metrics is Frechet inception distance. And that was just somebody took two measures, approximated them by Gaussians, and then incorrectly implemented the formula for the OT cost, the Wasserstein 2 cost between the two. And that is now the standard, one of the two standard metrics. So, I'm not saying this to be critical, rather to say that there's a contribution that can be made in looking at these metrics, right? Not even solving the problem better, but proposing a metric. Of course, really the challenge with generative models is you're not minimizing a loss, okay? You can't compare two different models and say one is better than the other, because unlike supervised learning, where you can just say this is the accuracy or this is the loss, in unsupervised learning, it's not defined. and that may be familiar to some of you in the case of image processing, right? Image denoising. We don't have a metric for the eyeball metric, right? So if I'm doing total variation image denoising, I can say that I solved the optimization problem and I got a different image. But, I can't say that this image looks more like it's supposed to look, other than comparing it to the original image somehow in some metric. So that's also the case with generative models. Okay, so enough about that. Let me jump into the talk. The talk will have a few different parts where I'll talk about the different projects, and they'll have different levels of detail and rigor depending on what I'm talking about. Now, the first one, I guess, that's closest to the topic of this workshop is this one, faster training of neural ODEs using optimal transportation regularization. And this is based on this paper from 2020, which was work with Chris Finley, formerly my postdoc. Now he's a scientist at Deep Render using these kinds of ideas. It's a startup in London, England. Levon Nerbekian, who's now a postdoc at UCLA and has continued this kind of work for Meanfield Games. And Jorn Hendrik Jacobsen, who was at Toronto at the time, and now he's at Apple. So as I said just a minute ago, we're trying to generate images, new samples from a distribution. It's an unsupervised learning problem, so we don't have a loss. People use surrogates, such as Frechet inception distance, which I mentioned, or just the training loss. And in fact, there's some recent papers, including one with the title like, do generative models know what they don't know, or something like that, that show that these models are not generating realistic looking images. They're minimizing the likelihood, but it's not necessarily mean that they look good to our eye. The alternative, of course, is the very popular GANs. But it's important to point out that GANs they're adversarial. They have a saddle point problem. And even for a student or postdoc who's quite good at training neural networks, training GANs is much harder. Again, because you're looking for a critical point, not a local minimum. And that's a topic of research and optimization right now. Okay, so what are generative models? This is Ian Goodfellow's brilliant idea from a few years ago. I guess 2014 already has 20,000 citations. It shows how fast the field is moving. And we've got very, very accurate looking images. This is a 2018 image from NVIDIA of GANs. So my understanding is that this is the first time people have generated images in the statistical way. So there was, generative model. So one approach that's different from GANs is neural ODEs. And it's very appealing because it's very mathematical. And there's essentially two components to this. One is this idea of a normalizing flow. So we're going to actually map, say, a Gaussian to our images, or vice versa. We're actually going to map images to a Gaussian distribution. We're staying in the same dimension. And instead of having a fixed architecture, like a ResNet, we're going to actually take gradients of an ODE. So you're going to implement adaptively an ODE solver. So the flow itself is an approximation of an ODE flow. And at any time, part of training your network can change the number of time steps or the level of interpolation from like RK34 to forward or whatever. That has some advantages in terms of, back propagation is done differently here. The adaptivity means, in principle, you can be selecting from the best network. So how the depth of the network is changing in order to best fit the loss. But it also has disadvantages. And one of the main ones is that unlike deep neural networks that can shrink the dimension as you go, you're stuck in a fixed dimension. And so it's actually more costly to train. Okay, in terms of generative models, a big advantage of this is that you're mapping noise to images and it's invertible. Images to noise and it's invertible. So the way to generate images is backwards from the way you train. Okay, and there's a lot of math background. So the idea of normalizing flows comes from Esteban Tabak, a mathematician at Courant. And then the neural ODE interpretation was Duvenow 2018, and also around the same time, Haber and Rothoto, two mathematicians as well. The first implementation of neural ODEs for generative models rather than classification is Duvenow in 2019. It's called Fjord. And the work I'm going to talk about is essentially a regularization of Fjord that speeds up training significantly. And up here you see, first time as a mathematician I've ever been tweeted. So our paper got a lot of attention on Twitter, for whatever that's worth. I think it's kind of funny. Anyhow, what's the idea? Okay, the key thing is when you have a mapping from one density to another, you have, and you're doing an integral, you have the change of variables formula. So you have a Jacobian that you want to compute. That requires computing, if you're in Lagrangian coordinates, a divergence in high dimensions. Okay, so the density estimation problem to learn the generating distribution is here. The first term is the log likelihood. It's the standard term. And the second term is reflecting the fact that when we change variables by a mapping, you have to compute the change of volume of an area element as you go. And this particular one is written in, like I said, Lagrangian coordinates, so you have a divergence. To generate images, you're going to, once you have the velocity field that you're looking for, you're going to sample the normal distribution and solve an ODE. Okay, to train, as I said earlier, you're going to go the other way. Try to map images to a Gaussian and optimize the likelihood as well as the change of variables, how that changes the density. Okay. Oops. Okay, so the good idea was using ODEs as an architecture, allowing adaptive architectures. But what we didn't have control prior to this work is that nobody said, let's penalize a Lipschitz constant. So the loss was over all vector fields. But as you know, there's more than one way to go from A to B. And if you go in a very wiggly way, so if your velocity is changing a lot, the Lipschitz constant of your velocity field can be large. And it makes sense if you know ODEs that that's going to require more time steps, be harder to solve. So what we said in this paper was, well, why don't we try to find, of all possible velocity fields, the one that has a better Lipschitz constant. So we put in a penalty for that term. And this is kind of a schematic illustration of the wiggly paths versus a smoother path. This is the idea going from this to this picture of essentially straight line paths. So how is it done? We added two terms in the objective to encourage regularity of the trajectories, one for a penalty for the size of the velocity, and one a penalty for the size of the gradient of velocity. These are pretty natural terms to put in. They do have a cost, however. If you're aware of training neural networks, anytime you put a derivative in, like a v sub x term, then you have double backprop, it's called. You're taking a derivative of a derivative, so two derivatives, because when you're training, you're taking a derivative in w. If you do this naively, it's going to slow down training a lot, and it's not worth doing. But we found a simple way to avoid that cost, which what amounts to is finite differences. So we don't use backpropagation to compute these gradients. We use a finite difference, and that allows us to, it's called detaching the derivative from the computational object, essentially avoid double backpropagation. In addition, there's a high dimensional gradient which you approximate using random projections, using Johnson-Lindenstrauss lemma, which says I can approximate this vector with a few projections. So these tools are sort of, they're not standard now, but there's tools that we used in other projects, and so it wasn't so difficult to implement them. Okay, now there's a connection with optimal transportation, in particular the Benamou-Bernier Lagrangian formulation. It's a very close connection, which is nice, which is that the Benamou-Bernier formulation says you're minimizing, f squared rho dx dt subject to the constraints. And our loss has the same velocity penalty. You don't see the rho in there, but it's in there because it's a particle approximation. But a weak form of, well, really, the most important part that's missing from GANs and all these models is this 19D constraint. The fact that you're actually mapping one measure onto another. So one of the defects of GANs is what's called mode collapse, which is essentially, in the extremes case, your model could just memorize one image, right, and just repeat that image again and again. Or in the less extreme case, it's just mapping some images. So the quality of the images is high, but you're not getting sampling from the full distribution. Now, this final constraint in high dimensions is very hard to implement. What we have instead, the way it's implemented here, is a soft version of that, which is to say that when you map from images to your Gaussian, you're going to measure the likelihood of those images. When you go backwards, we're mapping from a Gaussian to images. There's still no absolute guarantee that you've covered the entire distribution. I don't know of any way to do that, but this seems to do somewhat better.
Can I ask a question?
Yes.
So in the previous slide, you were mentioning about regularizing the Hessian, right? But from OT, we know that there are like transport maps that are not really C2. So
it's not
like, for example, if you split a mass, right? So how should I think about this? Or what's the benefit of regularization?
It's the Jacobian, not the Hessian. So because it's the Lagrangian formulation, we have a velocity field. And
yeah, but the velocity is the gradient of the Bernier potential, right? So that this is the second derivative.
Well, I mean, we're taking one derivative, and it's true. Look, we're not even, these are strong solutions that we're roughly approximating, but there's no claim of any kind that we're really solving the OT problem. It's just a nice analogy, essentially.
I see. Thanks for clarification.
Just to chime in here, wouldn't that gradient be just like viscous friction, like what was studied in by, let's say, Bernier, Otto, and Seiss? Right.
Yeah, I mean, big picture, it's cute that there's connection with optimal transportation. I think the important thing is to go back to this picture and just say, if you have an OD model and all you care about is nothing in between, just where you started and where you get to, then all things being equal, you would want to penalize regularity of the velocity field. If you don't do that, you're going to have very wobbly trajectories. So we found some way to do it. I'm not saying it's the best way, but we found some way to penalize that. And really the only claim I'm going to make is that when you do that, you get the same quality of solutions as before, but it trains about 20 times faster. And I think there's a clear intuition why that should work, because before you had no penalty on wobbly velocity fields, which we know slow down OD solvers. And now you've penalized that, but not so much that you've impacted the loss function at all. And like I said before, the OT connection is cute, but we know we're not really solving the OT, and none of these models are. The main reason is this 19D. So nobody is making sure the most important part, that one measure, is being pushed onto another. Even if we assume strong solutions exist, right? In anything people are doing, there's no way to ensure you've captured all the images. So.
Hi. In your previous slide, when you said that you use, to avoid double back propagation, you approximate the derivatives using difference quotients. So I guess I have two questions. Question one is, does it happen that you have noise and this approximation is bad? And if yes, does having a good approximation of this derivative influence your results?
That's a good question. So I guess the question, to rephrase it, is do finite differences perform better or worse than symbolic derivatives? Yeah. So in our experience, and Chris is really the expert on this, he compared it pretty carefully. And he found that finite differences work better than backpropagation when we're talking about derivatives in X. In fact, there's no guarantees that backpropagation is perfect either, right? It's symbolic derivatives of something that could be 50 layers deep with a lot of non-smooth parts, where it's not differentiable. So we did some sort of scientific computing style experiments a while back and found we actually got more accurate results with finite differences.
I see. Thank you.
Yeah. Okay, well, thanks for the questions. It makes it a lot more enjoyable to give a talk with questions. So I'll keep going. So yeah, so the punchline is not a math punchline, it's just a practical punchline. But actually, this is a paper that when we sent to conferences, people liked more than a lot of our other stuff because we have a clear curve that says it's faster. And this was something people cared about with these types of models. They cared about the fact that it was a big complaint of these models is that they're so much slower. And so this helped with that. And that's essentially the main story I wanted to get. Here you see training time comparing MNIST and CFAR. And since this paper has come out, we've also trained larger dimensional models. Okay, so that's kind of the story of this paper. It's very hard when we send these papers out to conferences, you know, you've probably heard from other people that the referees can be very all over the place. Sometimes they're young graduate students. There's always a few good referees and a good area chair, so not to disparage them at all, but it's a ton of work to review these papers in a few weeks. You might have 10 papers to referee. So you never know what to expect. And so this paper was one of the lucky ones, I guess, which is great. Here is the requisite generated images. They're not such great quality images, but like I said before, we are not really enforcing the eyeball norm. It would be great if somebody had a way to do that. We're not even, and what's funny, I was thinking about this before my talk today, is that GANs, right, adversarial, GANs are saying, I have an adversary that's trying to guess if a given image is, you know, generated or drawn from the distribution. That's not even that statistical, right? If we're doing statistical learning, you would think that a GAN would say, take some distribution of features of a batch of images and see if that distribution is consistent with the distribution generated versus sampled. But GANs don't actually do that. They're just really trying to eyeball it. So there you go. Okay, let me move on. Are there more questions about this, or I'll go to the next topic. Oh, this is ImageNet. I guess we did do simulations of ImageNet here. And you see, again, if you look closely, they have some weird patchy bits. But I guess at the time, this might have been the first time neural ODEs could do ImageNet. So it's still significant. Okay, so I'll start a new topic, unless there's any questions. No? Okay, so
just one quick question. So the representation of images you used with your flow was just the intensity, pixel intensities, right? There was no other layer of complexity there, right? Okay, thanks.
Yeah, everyone's just weirdly just looking at the statistics of the last layer. Just the images, just the pixels. There's no statistics in between.
Right, thanks.
Yeah. Yeah, and that's a good question, because why not use the in-between layers as features? Mathematically, it makes sense, right? But there's a practical reason why people don't do that, which is that in the software, it's easy to output the weights for all the layers, and it's easy to output the last layer's outputs, but it's actually a real pain to get the outputs at other intermediate layers. So people just don't want to do that. Okay.
I also have I have a question for this result. So you mentioned that before we just observe these points, like these images, and then you want to kind of interpolate to get a whole distribution.
Yeah.
So in what way that we can know that we have done a good job. So is there a mathematically well-defined way to check that?
No, and I was comparing this earlier to, say, total variation denoising, right? You start with a noisy image and you generate a clean image using a minimization. So you can measure how well you minimize that TV loss. But essentially, to tune the model or to say it's better than some other denoising, say Gaussian smoothing, it's just your eyeball metric. There's not a metric that says these images look more realistic than those. Not one that I know of anyways. And so with GANs, people are really cherry picking the best images that they were able to generate and plotting them. And for all you know, unless you're going to look through the million images in the database, they could have just copied an image that was already in there. Just because I don't recognize the celebrity doesn't mean it wasn't already there. It could be very similar. No, this is, I think, not a critique, because look, we did it in image processing ourselves, but rather a challenge. In fact, what I was saying earlier is that even the metrics that are used are pretty deficient. So I spoke to a colleague about this. I said, look, should we fix the formula for the distance between two Gaussians? Or two Gaussians? And he said, well, if you have a paper that does something good and along the way you mention this is the right formula and it makes a difference, then sure, do it. But other than that, getting people to change their standards is hard to do. So yeah. So I guess where we were lucky is we could just focus on one thing, speed, add a regularization term that was mathematically motivated, and improve the speed. That's our only contribution. But GANs are pretty non-rigorous in general. Okay, on to the next topic. I'm going to speed up for this one because I want to cover a bit more. It's about adversarial examples and certification. So certification means giving a guarantee that in a neighborhood of a certain image, there's no adversarial examples. In other words, if I classify an image a certain way, there's a ball, a Euclidean ball, say, around that image where all the images have the same classification. That's a hard guarantee to give for standard neural networks because we have no control over their derivatives. So a neural network can be piecewise constant, have a huge jump and change classification, and there's no local way to control that. So what happened? How do you get around that? Well, the first is empirical. A practical thing is to do adversarial training. Let me focus on the theory of adversarial training. Statistical learning, so training classification of a normal neural network, is just saying I want to minimize the loss under images generated by a certain distribution. But it says nothing about adversarial attacks, right? There's no worst case training, it's expected case training. Okay. Adversarial training is approximating robust training. Robust training would say, let me minimize the error of, the worst error in a certain ball, right? That's robust training. Minimize the expected loss, where the loss is measured by whether there's any errors at any points in a ball of a certain distance. Of course, globally searching that ball is too costly. It's not feasible. So instead, what adversarial training does is does a few steps of a gradient ascent to see if you can find an adversarial image. And then you train on that. Okay, so I think adversarial training makes sense. Again, it's easier to be rigorous because we're doing supervised learning. So what's a certified model? This is a cool part. So everybody here, or many of you anyways, know the fact that if I take a bounded function and I convolve it with a Gaussian, what can I say about the gradients of the convolved function? Anybody? Help me out. Right? Take a bounded function, convolve it with a Gaussian. When I differentiate a convolution, I can put the derivatives on either function. So I can prove a bound on the max norm of the convolution using the maximum of the gradient of a Gaussian. So that's roughly 1 over sigma, where sigma is the variance. So from that fact, if I had a model that was convolved with a Gaussian, I'd have a gradient bound and I could prove robustness. There's also a probabilistic version of this argument as well. But the point is, if you define this equation 2 here to be your model, then you have certified robustness. And this was a pretty influential paper by Cohen, who did this, although he made a probabilistic proof where the models vote rather than average. But later Solomon did the analysis with averaging. Well, the good and the bad of this is this model is no longer deterministic. So F smooth now is not given by evaluating f of x anymore. It's given by taking 30 or 3,000 random perturbations of x and evaluating them all through a network, which has some downsides. One of them is the cost of inference. The certification step also is costly. So our contribution was this, and it was kind of motivated by an interest also in solving PDEs. It's to say, is there a way that we can have a deterministic model, which is roughly approximately equal to F smooth? So can I train a model to be the convolution of F with a Gaussian? Keeping this in mind that in high dimensions, there's been some very interesting and promising work on solving PDEs, but so far nothing with a convergence proof. And we also don't have a convergence proof. So there you go. So here are the challenges. It's the cost of inference, like I said earlier. And the idea of training, actually, this goes back, well, it goes back a long way, but we wanted to show a connection with previous work in neural networks. And Bishop observed in the mid-90s that adding Gaussian noise is formally equivalent, let's say, to some kind of gradient regularization. This statement is not quite rigorous, but you can make it rigorous. And essentially what we did is to go the other way. We want to build a model which is equivalent to Gaussian noise being added. And so we solve a regularized problem. So that's what we do. There's a few tweaks on it, but it's essentially, we take the original model, we train a new model to match its outputs with an L2 cost, plus we regularize the model, we make the gradients small, and that's this loss that you see here. It's not exactly Gaussian convolution, but if you do this iteratively a few times, it's like a finite difference approximation to the heat equation. Or you could just say, we're doing this this variational form, which has, as Euler-Lagrange equation, Laplacian u equals f minus f star. Okay, I said that wrong, but I meant there's an Euler-Lagrange equation for this with the Laplacian. Okay, so that's what we did, and how does it work? It works. Basically, it works as well as, you know, the other things that are being used currently. So the main thing is, you can avoid the stochastic step and get a model that has certification bounds that are just as good as before or better, without having to do multiple inference steps. And in the table below, we compare the cost of inference on GPUs and CPUs. So it's, well, you can see from the table, it's quite a bit faster on both, basically, as you'd expect from essentially, this table is measuring the relative cost of doing inference 30 times versus once on different hardware devices. And this is important because there's an interest in putting models on your cell phone, say, where inference cost is important. Okay, so that's it for that topic. Dayan or Jeff, do I have 10 minutes left, or how much time?
Yeah, you have about 10 or 15 minutes is good, yeah.
Okay, I'm gonna do one more topic. Oh, and just to mention, we also use this finite difference idea here for the regularization. Again, we want a Jacobian. That's a high dimensional one, not just a gradient. And we use Johnson-Lindenstrauss to approximate it by projecting with random vectors. So it's finite differences plus random projection. And that works well, even if Johnson-Lindenstrauss might say you have to use 30 vectors, but you can get away with a lot less because you're also doing stochastic gradient descent. So each time you're hitting it with a different vector. Okay, now I'm gonna do another topic, which is a little bit different. It's about optimization. And it's from an ODE for Nesterov's method to accelerated stochastic gradient descent. So I'll try to just give it, actually, there's one key calculation I'd like to show that for people who are already aware of this stuff, you might find interesting. So I'll skip a little bit faster through this background stuff. So Nesterov acceleration is a super popular method from the 80s. Itself is based on Polyak's heavy ball method, which is local. It works for quadratic functions or local for functions in general, whereas Nesterov has a acceleration proof for all convex functions. One example in the convex case, another in the strongly convex case. And recently, some influential people in the field were pushing for, a better understanding of this algorithm because the proof is not so insightful. But really their goal was to build new algorithms, new accelerated algorithms. And these papers hadn't yet succeeded too much in a major way of doing that. Oh, where did I go? So there's a picture of why for poorly conditioned functions, gradient descent can be slow. Nesterov's method is faster because it goes from one variable to two variables. And there's this momentum interpretation. But generally, I think people would agree it's kind of hard to understand the motivation for Nesterov's method. It's not exactly the same as the heavy ball. But there's, there you go. So what we did, there already was this Su, Boyd, and Candes ODE that you see here, x double dot plus 3 over tx dot. What they showed is that if you discretize this ODE, you can recover Nesterov's method. This is not such a surprising result. What they did was for the convex case. In the strongly convex case, you can go back to the heavy ball ODE, which is physical, and see that that's quite similar to Nesterov's method. Okay, so that's fine. So what did we do? Sorry. So let me just, before I tell you what we did, tell you what we did with it. So formally, stochastic gradient descent is a discretization of the gradient descent ODE, where you decrease time at each step. So we said to ourselves, can you have an accelerated stochastic gradient descent by taking an ODE for Nesterov's method, accelerated gradient descent, and similarly decreasing time? And the answer is yes, and we used a Lyapunov function to prove it, that you're decreasing the Lyapunov function. And just to mention what the function is, for gradient descent, you can use the function itself, f, or the distance squared to the minimum as a Lyapunov function. For accelerated gradient descent, you have two variables, and in combination, they decrease the Lyapunov function. So it's f, oh, I'm missing a constant here, plus a constant times v minus x squared is your Lyapunov function. So Nesterov's method doesn't necessarily decrease the function at every step, but it decreases this energy, essentially. So what we did was we took a different ODE, and what you have here is an extra term that's not present in the Su-Boyd one. And if you actually evaluate this, it gives you a Hessian term that wasn't there before. Okay, although afterwards other second order ODEs have been studied, really that's not the most important part. The important part is what you get in discrete time, not continuous time. Okay, so now let me show you the cute part. This is kind of the main part of this. I'm going to tell you what happens in non-stochastic gradient descent, and then explain later how a similar thing happens in the much harder to analyze situation of stochastic gradient descent. So let me motivate a derivation of Nesterov's method as follows. Right up here, the first equation is vanilla gradient descent with the right time step or learning rate of 1 over the Lipschitz constant of f. Now let's suppose that we double the variables, so introduce a new variable v, and instead of doing gradient descent for v, you make it faster. You make it 1 over w times too fast. By itself, this equation is unstable. It won't decrease f at all. But let's do a few things now to drive Nesterov's method. Let's reduce to one gradient evaluation by taking a convex combination of these two variables. And it'll be parameterized by w. In addition, let's add a coupling term, which says let's compromise by pushing x towards v, the fast variable. When you take those two steps in this derivation, you get the three equations I have here. The x update is just gradient descent plus a force proportional to W pushing you towards V in the direction V from X. You have the faster V variable, and then you have the Y, which is a convex combination of these two variables. And that's where you're going to evaluate your gradient. So you evaluate the gradient at Y. That's it. That's the algorithm we propose. And on the next slide, I'll show that if you, oh, no, I don't. If you take this algorithm that I just wrote down and then eliminate one variable, eliminate the V variable, which is about 3 lines of algebra, then you get Nesterov's method once you make the right choice of W. And that's the story. And a similar derivation works for the strongly convex case, very similar. Again, 3 lines of algebra. And again, you've derived Nesterov, and this is different, a different way to do it. The nice thing about doing it this way is that if you keep the 3 variable case that I put up here, the system of first order finite difference equations, essentially, this decreases the Lyapunov function. And now if you add a time parameter and slowly decrease time, you get an algorithm that works in the case of stochastic gradients and gives you an accelerated stochastic gradient descent where you can prove it converges with a faster rate constant than you would get for vanilla SGD. So here's, so obviously I wouldn't expect you to absorb this as I'm flying it by, but just to tell you the idea of it, this H parameter, H over T, is replacing W, where now we have a variable time step. Here's the proposition that you recover the standard Nesterov in the convex case. And by allowing for stochastic gradients, we get a stochastic gradient inversion. And again, we can prove a convergence rate by essentially bootstrapping the convergence proof in the non-stochastic case. So finally, how does this relate to existing algorithms? So what's the use of this proof? So we proved something about an accelerated stochastic gradient descent. Does that mean we have a new, faster algorithm than was out there before? No. What it means is people were already using a heuristic accelerated gradient descent, which was adding momentum and guessing the parameters. And that's what's here in purple, momentum SGD. But there was no proof that this method, which works very well in practice, better than SGD, there was no proof that this method is actually faster than vanilla SGD. What we showed is that a very similar algorithm, it's not the exact same constants here, but it's quite similar. The one we derived with the 3 variables, you can reduce it to 2 again in the stochastic case, and it looks somewhat like this with an extra term. That's the one that we prove is fast. So it gives some justification for using momentum SGD. Now, numerically, when we run it, the results we get are kind of tricky to assess because it's very hard to meet worst case rates, but essentially it performs quite close to momentum SGD, and it comes down to how well you can tune it, which can be tricky, even in simple cases. So again, there isn't really time to go through the details, but we have a proposition that says under slightly different assumptions than existing work, we get a faster rate constant. And in the case of SGD, the rate is so slow that having a smaller constant actually does make a difference. You know, because the 1 over K rate means you might have to do 10 times as many steps to get 10 times the accuracy. So having a rate constant that's 10 times smaller means it could be 10 times faster to get the same accuracy. Okay, I think I'll stop there. Thank you. I know I squeezed a lot in, but that was a choice I made, and I hope you liked it. Thanks.
All right, thanks, Adam, for the really fascinating talk. If there are any questions or any more questions from the audience, please feel free to just jump right in and unmute yourself, or you can raise your hand or type them into the chat box.
Well, maybe we could do questions in the breakout session too.
Yeah, since there were already questions in the talk, we can also, if there are no questions right now, we can also move to gather.town. So I'll just give people a couple more seconds to chime in if you want to ask a general question.
And I'll answer questions about anything, not just. Sometimes people want to know what it's like trying to jump into this field from math. I'm happy to discuss that a little bit too, maybe off the record, depending.
I mean, maybe I can ask one question about the last chunk of the talk here with the Nesterov acceleration. Like, is there any reason to believe you can get better acceleration than this, or are there like theoretical results that say that the rates that you're seeing from Nesterov are optimal in some sense?
Yeah, that's a good question. So, so I think, as you know, in the deterministic case, there's worst case, like lower bounds that say you can't do faster than Nesterov in terms of in the class of functions that are, say.
Yeah.
In the stochastic case, prior to this, there are information theoretical bounds that say you can't do better than, say, 1 over k in the strongly convex case, 1 over square root of k in the convex case. And we didn't do better than that. But what's happening is people are just working on the rate constants. Okay. So if I go to the table, I think I have it here. Hang on one second. Yeah, so here's a table in, this looks like the convex, both cases. So the first one is the strongly convex case. 2009, 2013, 2019, you see these different rate constants. And the G squared is like L plus sigma squared. And so Nesterov's method in the deterministic case improves the dependence on L and mu. And here in the stochastic case, we don't get a faster rate, but we get a better rate constant. And you've essentially dropped the L. So think of it this way. When you start off SGD, the very first step has to be 1 over L or less, right? But that L doesn't come into the algorithm ever again because you're shrinking the rate.
I see.
So we've dropped it from the algorithm. So yeah. And that's basically it. And then in the convex case, similarly, you have a 1 over square root of k rate. There's a log factor. Now, other algorithms have gotten rid of the log factor by assuming the actually realistic assumption that you've planned ahead of time how many steps to take, and then doing different analysis based on that. But when you keep the log factor, again, we drop the dependence from G squared to sigma squared, which can be a lot smaller. The other interesting thing about this algorithm is the learning rate is always order 1 over k for the strongly convex case. It's basically, it starts at 1 over L and then shrinks like 1 over k. But this algorithm, and Nesterov's method takes bigger steps.
Mm-hmm. Yep.
This algorithm has instead of square root k learning rate, it's k to the 3/4. So it's quite different, and I think it's never before seen rate for SGD. Yeah, but are there lower bounds on the rate constant? No, I don't think so.
Okay.
So Adam, can I ask one more question? In practice, SGD and similar algorithms are used in highly non-convex cases too.
Mm-hmm.
Do we learn anything from your story about that?
I mean, this is a good question because it's about modeling, right? The way I look at it is that for many algorithms, you're going to eventually get to a local minima, and that's where the convex analysis kicks in. That's the justification. There was some popular discussion of the non-convex case about saddle points and our algorithms getting stuck in them, for example. But short answer is no, the non-convex case, there's no analysis here for that because this is a global rate. So don't have much to say there. There are proofs for SGD about rates, slightly different results, like how quickly you get to a critical point or to a neighborhood of a critical point for the non-convex case.